final topic of discussion for this class is the singular value decomposition. This is the matrix factorization that's behind PCA. In this lecture, we're really not learning anything that's new to us. It's something we've been using the whole time. The singular value decomposition is really more of a theorem, and it says that any n by p matrix X with rank R, and now typically in data science, we're hoping that our matrix is full rank, meaning that the rank is equal to either the number of rows or columns, whichever is fewer. Because remember, a full rank matrix has to have either linear independent rows or linearly independent columns. Okay, so for any matrix X, there exists orthogonal matrices U and V, and a diagonal matrix D that has diagonal elements called sigma 1, sigma 2, up to sigma R, such that X, again, this would be our data matrix, is equal to U times this diagonal matrix padded with zeros times V transpose. Now, again, this is in the statement of the theorem. They just decide to call this thing V transpose. Why? Well, because the rows of that matrix are what's interesting to us, meaning the columns of V. I think it helps to illustrate this. If X is n by p, just for the dimensions to all work out, U must be n by n, V must be p by p, so this in-between matrix has to be n by p. So it's a diagonal matrix that's padded with zeros. Now again, I said we're usually full rank. So in this case where we have a skinny data matrix, which is our typical case, R would equal P. And so I would really only be padding zeros onto the bottom of the diagonal matrix here. Now, when I write it this way, these zeros that are padded in this tall rectangular matrix, when I multiply this all out, these zeros are actually just going to completely eliminate the bottom rows of V, leaving VR. And these zeros, when I kind of pick up this matrix and pull it over here and pull it down the columns of U, is going to eliminate the right half of the matrix U. So everything that's got stripes here, red stripes, goes away because of all those zeros. Now, again, if R is equal to P, I don't lose anything in V. I have a full rank matrix. And that leaves me with what's known as the skinny SVD. Okay, again, R should be equal to P because our matrix should be full rank. Now, this diagonal matrix, those elements along the diagonal are called singular values. Singular values are always ordered from largest to smallest, and they are greater than 0. V contains the matrix known as the right singular vectors, and U contains the left singular vectors. And what we're actually going to see is that when X is a data matrix that's centered or standardized, these V's are just the principal components. They're the eigenvectors. And these U's are the standardized scores. If I multiply U times D, what I would get is the scores. So we'll get into that here in a minute. Some fun facts about the SVD that you would find from any textbook pretty much immediately after it's presented is that the right singular vectors, those are the rows of V transpose, are the eigenvectors of X transpose X. So remember, X transpose X is what is the definition of a covariance matrix as long as X contains centered data. Now, of course, there's a multiplication by 1 over n minus 1. Again, I ignore all those constants that are out front. It's just a constant. Left singular vectors, those columns of U, turn out to be the eigenvectors of x transpose. So there's another weird thing going on here where the scores actually turn out to come from eigenvectors of x transpose. Now, we don't have to get into that. I would rather you have a full understanding of what coordinates and the basis vectors and all that represents. But the singular values are just the square roots of the eigenvalues. So x transpose and x transpose x have the same eigenvalues. That's another theorem. So I'll rehash this, what I just said verbally. If x contains centered or standardized data, then x transpose x is the covariance or correlation matrix, respectively. And the singular vectors are principal components. So it's PCA. It's not different. SVD is PCA when x contains centered or standardized data. So in order to see that, let me just show you how the matrix factorization typically works out. Usually the matrices U and D are multiplied together to form the scores or the coordinates. And the matrix V is the set of basis vectors. So the factors, principal components, basis vectors, those are all words for the same thing, the columns, or the rows of V transpose. So right now, I would like to flash back through a couple of lectures and pull up some slides that we've seen before. The first came from the PCA recap. This was actually part of an optional video. And we were looking at principal components as a matrix factorization. So we had the scores times the eigenvectors. When we talked about principal components, we talked about how to get the coordinates in the new basis. So the scores were equal to x times v. Well, so that's two different equations with the same exact objects in them. X is equal to s times v, and x times v is equal to s. Well, if you remember, we also did this funny math example when we talked about orthogonal matrices. So this is another flashback to the orthogonality lecture. And I was showing you that an orthogonal matrix is easy to maneuver inside matrix equations, since the inverse is equal to the transpose. And I showed you this form where we're moving around V and U. Well, that's exactly what's going on here. V is orthogonal, so if I multiply both sides of this equation by its inverse, V transpose is orthogonal, so the inverse is V. If I multiply both sides on the right by V, I get this equation. So it all connects through the orthogonality back to the SVD. And the main point I want you to be picking up on here is that principal components is the SVD. It's the singular value decomposition on centered or standardized data. Now, if you don't center or standardize your data matrix X, you can still perform the SVD. But what you talk about in that scenario can't be variance, because variance involves the sum of squared distances to the mean. And if we don't center our data, the mean is not at the origin. And so instead, we're just talking about sum of squared distances to the origin, but not the mean. And so in a sense, there's not much difference at all, except the interpretability can't be drawn from all the theory of principal components of a actual normally distributed data. And so sometimes practitioners do opt for the regular uncentered SVD rather than PCA. This is true especially in applications like genomics, text, or image analysis. And we'll go into an example here in a minute.